far more efficient than preventive maintenance. It's far less destructive than running to failure. It's able to perform unbelievable equations in a single moment. With capability rivaling Superman's X-ray vision, it peers into plant machinery and assesses specific mechanical and electrical faults quickly and accurately. Is it magic? Not at all. It is vibration analysis. Some personnel have formed unfair or inaccurate opinions about vibration analysis, considering it to be some mystical black box magic. Welcome to CSI Training. This program unveils the black box mystery and demonstrates the value and simplicity of vibration analysis. Whether you are directly involved in a vibration program or just have an interest in the subject, we are sure you will benefit from the information and concepts presented here. Vibration analysis is a real benefit to industry today because of the ability to see what is happening inside a machine without interrupting its process in any way. Among the many mechanical and electrical problems that vibration analysis can determine are unbalance, misalignment, bent shaft, rolling element bearing defects, bearing looseness, loose bearing mounting, structural looseness, resonance, gear wear, gear misalignment, cracked or broken gear teeth, belt wear and looseness, chain wear and looseness, shield runout, cavitation, fluid and airflow problems, sleeve bearing wear and looseness, oil whirl and oil whip, tilt pad bearing wear, and most electrical problems. Simply put, vibration analysis can be utilized to determine the source of just about anything that can cause machinery or production downtime. In order to successfully use vibration analysis to predict a machine's condition, we must have a basic understanding of how the vibration data represents the occurrences within the machine, and of course the terminology associated with vibration analysis. Vibration not only affects industry, but we are aware of it in our daily lives as well. For example, as you drive your car, you tend to notice any abnormal vibration, and may purpose to have the tires balanced to see if that corrects the vibration. Let's take a look at an unbalanced car tire as it rolls along the highway. Assume this tire has an unbalanced weight or heavy spot at this location on the tire. As the tire rolls along the road, we will trace the path of the unbalanced weight. As the tire rolls 1/4 turn, the trace moves from the top position to a point in line with the center of the tire. The trace of the path has moved to the right because the tire is moving along the roadway over time. As the tire rolls another 1/4 turn, the trace moves further down and to the right. Again, it is to the right because this occurs later in time. The trace of the unbalance has now moved up to the center line of the tire, but is still to the right. The tire completes one revolution so that the unbalanced weight is at the top. This, then, is the trace of the path the unbalanced weight makes during one full rotation of the tire. As the tire continues rolling down the road, the trace repeats the pattern for each revolution or cycle. The horizontal or x-axis shows the time it takes to complete one cycle or revolution. The y-axis shows the amplitude, or how much the unbalance moves during each rotation. Although we've been referring to this path of the unbalance as a trace, the technical term for it is a waveform. It is made up of the individual sine waves of the vibration of the machine, or in this case, the tire's unbalance. The analyst uses the waveform to indicate certain characteristics about a machine's condition. The analyst can view the same data from another perspective to gain additional information about the machine. If we view this waveform from the end, it becomes a single line. The technical term for this view of the data is a spectrum. The y-axis here is amplitude, just as in the waveform. The amplitude for the spectrum is dictated by the amplitude of the waveform. The x-axis is frequency, which tells us how often something occurs. This is done mathematically by computing the time for one cycle in the waveform. On the waveform generated from the unbalanced tire, we can measure the time it took to complete one revolution, since the x-axis is time. In this case, It is measured in seconds. One cycle or revolution of the tire took 0.05 seconds. To obtain the frequency, we simply get the inverse, which is accomplished by dividing this time period, 0.05, into 1. This yields 20, which means that this unbalanced sine wave occurs 20 times a second. Multiplying this by 60 seconds gives us the number of cycles that occur in 1 minute. In this case, we see that it is 1200. In other words, the unbalanced sine wave repeats itself 1200 times per minute, which is 1200 cycles per minute, or 1200 CPM. Of these expressions, CPM is the most common in the field of vibration. On the spectrum, we can label this frequency axis as CPM, and the peak would be at 1200 CPM. Recall that after we determined the time for one cycle of the sine wave, we divided the time into 1 to obtain the inverse, which in this case yielded 20. This means that the sine wave repeats itself 20 times a second, which can be said as 20 cycles per second. This same peak in the spectrum can be referred to in terms of cycles per second, or CPS. It can be said then that this peak represents energy that is occurring 1200 times per minute, or 20 times a second. The technical term for cycles per second is Hertz, which is commonly noted as Hz. Hertz is simply a measurement of how frequently the cycle occurs per second. These two frequency units, cycles per minute and cycles per second, indicate the precise occurrence of energy, but the analyst often compares these frequencies to the turning speed of the shaft to pinpoint the source of the energy. As we were tracing the unbalance on the tire, we noticed that the unbalance created a sine wave that started and finished at the same time the tire did. In other words, the unbalanced sine wave completed one cycle every time the tire completed one rotation. In this example, the cycle for the sine wave is compared to the cycle or speed of the tire rotation. To express this spectral peak in terms of the speed of this tire, we can say that this peak represents energy that occurs one time every time the shaft turns once. This peak is commonly called a 1 times shaft turning speed peak. The unit used to measure frequency as a multiple of shaft turning speed is orders. In other words, this is a peak at 1 order of shaft turning speed. The frequency units are displayed in CPM, which is the number of occurrences per minute, Hertz, which is the number of occurrences per second, and orders, which is directly related to the turning speed of the shaft at the measurement point. There are times when one of these units may be more helpful than the others in looking for a particular fault. Other times another unit may be more helpful. Use them to maximize your analysis capabilities. We have used the unbalance of an automobile tire in the waveform and spectral data examples. Because we are really interested in industrial machinery and equipment, let's see how this applies. The same waveform and spectral data could be generated from industrial machinery that has an unbalanced problem. If the machine has other sources of vibration, they too would show up in waveform and spectral data. If this machine has a problem in addition to unbalance that creates a signal 2 times every time the shaft turns once, the energy from this signal will be added to the waveform. This new energy will create 2 complete sine waves during the time the unbalanced sine wave is created. Measuring the time it takes to complete one cycle, we see that it is 0.025 seconds. In other words, this cycle occurs twice as often as the unbalanced cycle. The analyzer processes this waveform signal and actually separates the waveform into 2 individual sine waves. The calculations are performed for each sine wave, which has the net effect of viewing the discrete sine waves from the end, which is the spectrum. The frequency of this new peak can be expressed in each of the 3 frequency units and can be said to show energy that occurs 2400 times per minute, 40 times per second, or 2 times during each shaft rotation. This 2 times peak is often called a 2-order peak. Here we can see how each of these peaks were generated because of specific mechanical properties. It is important to understand that there is a mechanical or electrical occurrence represented by every peak in the spectrum. The source of the mechanical vibration could be flow, electrical, or some other force. But the effect we measure is mechanical vibration. If this data was from a pump, a peak could show up which would equal the number of vanes on the impeller. The waveform here is more complex because of the added energy. Now during one rotation of the shaft, 7 complete cycles are generated. Again, the processing separates the waveform into individual sine waves. The calculations are made which convert this data into a spectrum. This new peak represents energy that occurs 7 times during each shaft rotation, 8,400 times per minute, or 140 times per second. It is common for machinery to generate many frequencies that create a very complex waveform, and thus many peaks in the spectrum. Determining the source of the peaks and the severity of the problem is the challenge for the analyst. Amplitude and amplitude units play an important role in detecting defects and determining severity. Let's use this go-kart on the slalom course to illustrate some concepts. If we view the go-kart from above, we can mark a trace of the path it is traveling. This trace resembles the trace of the unbalanced wheel. Let's return to the go-kart and let a photographer capture 3 pictures for us. The first picture we want is one where the go-kart is going the fastest or at its greatest speed. The background should be still, but the go-kart should be a blur. From here, we can see that the fastest speed is achieved in the straightaways and going either direction. Our photographer must capture the go-kart at the midpoint of the straightaway. The picture shows exactly what we wanted. We will label this picture maximum speed. The next picture we want is at the maximum acceleration. Acceleration is a change in speed. Maximum acceleration is where the driver would feel the most force as he attempts to keep control of the go-kart. The picture should show the tires rolling under and the driver straining to keep control of the cart. The greatest force occurs where the greatest speed changes occur. This is when the go-kart decelerates to reverse directions and accelerates to the maximum speed. Look at the force the go-kart is under as it makes the turn. This is a great picture of acceleration. We will label this photo maximum acceleration. The last picture we need is one which shows the total distance traveled across the parking lot. Not the distance that would be logged onto an odometer, but the distance or space covered from curb to curb in the parking lot. To show this, the photographer must use a time exposure for the time for one run from end to end. This will cause the picture to have the go-kart as a blur for its complete line of travel. The photograph shows exactly what we wanted. The go-kart is a blur the full distance of travel. We will label this one total distance. The previous 2 pictures show the maximum speed and the greatest acceleration. The trace of the go-kart shows the maximum speed at the midpoint of travel in either direction. The maximum acceleration is achieved at both ends of the trace. The distance is the total distance traveled back and forth. We have used this go-kart to illustrate the 3 units that can be used in measuring the trace or sine wave. In vibration, the units are the same, although they are called by different names. On this vibration trace or sine wave, the maximum speed is measured at the center point of the travel. The speed of a go-kart would probably be measured in miles per hour. The speed of a bullet is measured in feet per second. In the world of vibration, the distances are smaller, so we typically measure speed in inches per second. We usually don't refer to it as speed, but like the speed of a bullet, it is called velocity. In metric units, velocity is measured in millimeters per second. The maximum acceleration was captured at end of the turns or when the go-kart changed directions. In the vibration trace or sine wave, the maximum acceleration is measured at the same locations, the point of change in direction. On the go-kart, we measured acceleration in G's. In the world of vibration, the units are the same. Acceleration in G's, which is a measure of the force on a mechanical system. The distance the go-kart traveled was measured from the point it came out of a turn to the point it went into the next turn. The vibration trace or sine wave is measured in the same way. The distance the go-kart traveled could be measured in miles. Other distances are commonly measured in yards, feet, or inches. In the world of vibration, distances are not measured in inches, feet, yards, or miles, but mils. 1 mil equals 1/1000th of an inch. And in the world of vibration, the distance is called displacement. The amplitude units and where they are measured is a concept that needs to be understood. And though the way we presented them is oversimplified, the theory applies. We need to realize there are 3 waveforms. In our examples, we have been using a displacement waveform. The other 2 waveforms are a velocity waveform and an acceleration waveform. This displacement waveform has an x where the maximum velocity is measured. The velocity waveform is created by mathematically moving the highest velocity to the top of the waveform. Notice that this new waveform does not overlay the displacement waveform, but is ahead of it. For this reason, velocity is said to lead displacement. The acceleration waveform is created by mathematically moving the maximum acceleration to the top of the waveform. Notice that this waveform is ahead of both the displacement and the velocity waveforms. For this reason, acceleration is said to lead velocity. It's not important to understand how each waveform is mathematically derived, but it is important to know that the 3 exist and to know the industry standards for measuring each. The displacement waveform shown here is measured from the top peak to the bottom peak. The industry standard for displacement then is peak to peak. This waveform then would indicate vibration of 6 mils peak to peak. This velocity waveform is measured from the 0 or center line to the top of the peak. The industry standard for velocity is peak, and this waveform indicates vibration of 0.3 inches per second peak. The industry standard for measuring acceleration is RMS. RMS means root mean squared. This is a description of the mathematic procedure for calculating the value for this waveform. Actually, the process is reverse of the name. First, the values under the curve are squared. Then the squared values are averaged. And finally, the square root of the averaged value is performed. This means the RMS value of the peak is less than a 0 to peak measurement. It actually approximates 70.7% of the peak value. Remember that acceleration is a measure of force due to changing speeds or directions. It can indicate the force of impacting that occurs in machinery, such as when a ball impacts a defect in a raceway of a rolling element bearing. The go-kart example illustrates the 3 amplitude units of a sine wave. The distance or displacement is measured for the total curb-to-curb travel, while velocity measures the average speed for the distance, and acceleration measures the force in the change in speed or direction. We have pointed out that there are actually 3 individual waveforms, and that industry has established unique standards for calculating each one. Displacement is measured from the maximum positive travel across the 0 or at rest position to the maximum negative travel and is called a peak-to-peak measurement. Velocity is measured from the 0 or at rest position to the peak and is typically called a peak measurement. Acceleration is measured in RMS calculations, which is equivalent to about 70.7% of the peak value. Each of these units has a particular use in the field of vibration. The next section illustrates when to use them. There are particular uses for each of the amplitude data units: displacement, velocity, and acceleration. Viewing data in the various amplitude units affects the display and the analyst's ability to detect certain machinery characteristics. Let's look at some spectral and waveform data from a motor that has an unbalance problem and a bearing problem. This spectrum and displacement shows a predominant peak in a relatively low frequency equal to the speed of the shaft, or 1 order. It indicates the actual distance the shaft is moving during each revolution. The same data displayed in velocity also has a peak at one order, but there is a lot more activity in the higher frequencies due to the bearing defects. Remember that velocity shows the speed of the vibration. These peaks were not evident in the displacement spectrum because the vibration caused by the bearing defects is only moving minute distances. When the data is displayed in acceleration, the peak at one order has nearly disappeared, but the peaks in the higher frequencies are magnified because acceleration is a measurement of force. At shaft turning speed, the force or impacting required to change the direction of travel is minimal. However, with each revolution of the shaft, many components are coming in contact with and impacting the defects in this bearing. The force associated with this impacting as the components change direction is very significant. It is similar to the go-kart on a slalom course. When it is going slowly, the tires don't distort in the curve, and the driver does not have to strain to maintain control. At higher speeds, however, a lot of force is used in the curve to change the direction of travel. The extreme force is causing the tires to roll, and the driver has to strain to maintain control. It is important to note that the three spectra are the exact same data, simply displayed differently, to show the distances of the vibration, the speed of the vibration, and the force of the vibration. The displacement spectrum causes the analyst to ignore vibration due to bearing frequencies and other high-frequency occurrences. The acceleration spectrum may cause the analyst to ignore the low frequencies, which are often the root cause of bearing failures and other high-frequency energy. The velocity spectrum doesn't weight the low or high frequencies of the spectrum, so it is the unit of choice for viewing spectral data. The time waveform and displacement is similar to the displacement spectrum in that it accentuates the low-frequency occurrences. The time waveform and velocity shows both the low frequencies and the high frequencies, but it does not fully depict the impacting occurring in the machine. The acceleration waveform, however, is very busy with high-frequency energy. Because this data is indicative of the impacting within a machine, it is the preferred choice for identifying these destructive forces which accelerate machinery failure. To get the best of both worlds, view the spectral data in velocity, but view the waveform in acceleration to enhance your capability to determine severity. Spectral data is most commonly used by the analyst to determine a problem. The frequency or x-axis of the spectrum tells us the source of the problem, because every mechanical occurrence generates a specific frequency, as we will see. The amplitude or y-axis of the spectrum tells us how much, which is an indication of severity. As was pointed out in an earlier section of this program, the peaks in the spectrum are due to electrical, process, or mechanical occurrences in the machine that produce mechanical motion or vibration. This spectrum is displayed in velocity, which we have determined is the best selection for viewing spectral data. All the energy in a spectrum can be broken into three separate categories. The first category is called synchronous. Synchronous energy is all the energy that is an integer or whole number multiple of shaft turning speed. In this spectrum, the primary cursor is marking shaft speed, or the first order peak, and the other cursor markers are harmonics, or multiples of that frequency. Harmonic is another term used by the analyst to describe a characteristic of spectral data. A harmonic is simply a multiple of a given frequency. Harmonics are spectral characteristics that help identify machinery occurrences. We have already seen how imbalance creates a peak at one order. This three-jaw coupling with a worn insert generates a peak at three orders, or harmonics, of this frequency. The impeller with 5 vanes could generate a peak at 5 times turning speed and harmonics of this frequency. The 6 blades on this fan could generate a peak at 6 times turning speed, or 6 orders, and harmonics of this frequency. All of these are examples of synchronous energy. The second category of spectral energy is non-synchronous energy. Non-synchronous energy is all the energy above shaft turning speed that is not an integer or whole number multiple of shaft speed. For example, 2.5 orders, 3.2 orders, 6.4 orders, and so on. Non-synchronous energy is generated by rolling element bearings, process variables, electrical frequencies, and vibration due to other shaft speeds in a machine train that is not direct coupled. When collecting data on these fan bearings, the fan speed is the reference speed for calculating the order frequency and determining synchronous speed. We will start the fan and use this strobe to verify the speeds of the fan and the motor to determine whether the motor speed shows up on the fan point and whether this frequency is synchronous or non-synchronous. A strobe light can be used to identify fan shaft speed by matching the flash rate to the fan speed, which gives the appearance of freezing the shaft. It should be pointed out that the blades only appear to be stopped. All standard safety precautions for rotating machinery still apply. Here we can read the speed for the fan is 434 RPM. Strobing the sheave on the motor, we see that it stops at a speed of 1762 RPM. Since this is not a whole number multiple of the fan shaft speed, it would appear in the spectrum of the fan bearing as non-synchronous energy. This bearing in the pump generates non-synchronous peaks. Let's take a look at their approximate frequencies. This bearing has been marked, so we can visually determine the approximate frequencies. If a defect is at this position on the outer race, we can count how many balls will impact the defect during one revolution of the shaft. 1, 2, 3, 4, 5, and just a little more. 5 and a fraction balls impact the outer race with one revolution of the shaft. Notice that it is not exactly 5, but 5 and a fraction. This is the key to differentiating between bearing faults and other faults, such as vane pass, which would show up exactly 5 times for an impeller with 5 vanes. This fractional energy is called non-synchronous energy. That is, it is not a whole number multiple of the shaft turning speed, like 1.0, 2.0, or 3.0 orders. The inner race frequency can be approximated in the same way as the outer race frequency. With the reference marks lined up again, we will assume a defect at the mark on the inner race. As the shaft is turned, let's count the number of balls that pass through the inner race defect. 1, 2, 3, 4, 5, 6, 7, 8, and a fraction. We see here that the inner race frequency is also non-synchronous. Notice that the inner race frequency is 8 and a fraction, whereas the outer race was 5 and a fraction. A defect on a roller will also generate certain discrete frequencies, depending on how many times the roller turns over during one revolution of the shaft. With the reference marks in line again, we rotate the shaft one full turn and this time count the revolutions of the roller. 1, 2, and a fraction. This roller defect frequency, or ball spin frequency as it is commonly called, is also non-synchronous energy. In our approximations, we've shown that the ball spin frequency, the outer race frequency, and the inner race frequency are all non-synchronous energy. When data is collected on this motor, the motor speed becomes the reference or one-order peak, which is commonly called the primary frequency. It is here at a frequency of 1762 RPM. Notice that the harmonics miss this peak. It is a non-synchronous peak, and it is exactly 7200 CPM. This is a frequency equal to 2 times the electrical line frequency. This shows how electrical occurrences can generate mechanical vibration and that their frequencies tend to be non-synchronous. Here we have seen how non-synchronous energy may appear in a spectrum from other shafts or machine components, rolling element bearings, and even electrical phenomena. The third category of spectral energy is all the energy below shaft speed. It is called subsynchronous energy. Typical causes of this subsynchronous energy include belt frequencies, oil whirl on sleeve bearings, and shafts or components on gear or belt-driven machinery. When the speed of the belt is located with the strobe light, we can see that its frequency is 218, which is much lower than either the fan or motor speed. This means it will appear as subsynchronous energy for data from the fan or motor. When data is collected on this motor, there is a peak below motor shaft speed that is not related to the belt. This subsynchronous peak is the speed of the fan. These two examples show how energy from a belt or another shaft can be subsynchronous energy. Of the three categories of spectral energy, it is common for synchronous energy to be predominant. Causes for synchronous energy include unbalance, misalignment, coupling problems, vane pass or blade pass, gears, looseness, and other energy directly related to the turning speed of the shaft. Sources of non-synchronous energy include rolling element bearings, electrical frequencies, process variables, and energy from other components of the machine. Subsynchronous energy is typically due to belts, oil whirl on sleeve bearing machines, and other shafts or machinery components on belt or gear-driven equipment. Since harmonics are simply multiples of a given frequency, harmonics can occur for subsynchronous, synchronous, and non-synchronous peaks. Interpreting waveform data can be a key to confirming diagnosis, as well as a necessary tool in determining severity. The mere pattern of the waveform can give a clear picture of mechanical characteristics, such as impacting, rubbing, and transient occurrences. This waveform is in acceleration Gs, and the amplitude swing from a plus 3 Gs to a minus 3 Gs. This indicates severe impacting. The pattern seems to be symmetrical and repeats itself, so this indicates it is not just random impacting energy, but caused by a particular event or component. In this case, it happens to be the outer race of a bearing. This waveform is not symmetrical about the zero line. That is, its amplitude ranges from minus 12 to plus 8. This indicates a rub or impacting whose travel is limited. This third waveform here does not seem to have any repeatable pattern, but the amplitudes indicate severe impacting. This non-repeatable random energy is common with conditions like severe looseness, flow turbulence, or even the severe stages of bearing wear. We can see from these three waveforms that the patterns can help point us to the correct diagnosis. The amplitude in Gs is used to aid in determining the severity of the condition. For most garden variety pumps, motors, fans, and so forth that operate at speeds between 1200 and 3600 RPM, the impacting is usually considered severe when the waveform ranges from plus 1 to minus 1 or a 2G swing peak to peak. Again, the patterns and amplitudes of the waveform can help you confirm your diagnosis and determine the severity of a problem. Many concepts and applications have been covered in this program, which should provide a sound base to build on. Remember a few key points as you analyze data, because they will point you to the correct diagnosis. The first key is that the waveform is a trace of energy actually occurring in the machine. The waveform is considered raw data and is displayed in respect to time. The second key is that the spectrum displays the waveform energy after it has been separated into discrete frequencies. Each peak in the spectrum is due to mechanical, electrical, or process variables in the machine. The third key is how the three amplitude units affect spectral data. Displacement is simply a measure of the distance traveled, and since components cannot physically move as far at faster rates, the higher frequencies will be low in amplitude. The velocity data is a measure of how fast the energy travels, and it doesn't care whether the energy is a high or low frequency. In other words, velocity displays spectral data without weighting the high or low frequencies. The acceleration data tells the force of travel, including any impacting that may be occurring. Since less force is required for low-frequency occurrences, the low frequencies tend to be suppressed when spectral data is displayed in acceleration. The frequency units are displayed in CPM, which is the number of occurrences per minute, Hertz, which is the number of occurrences per second, and orders, which is directly related to the turning speed of the shaft at the measurement point. Some types of problems or faults are easier to determine when viewed with respect to the shaft speed. Other types, such as electrical, may be easier to determine using Hertz or CPM as the frequency units. Mechanical, electrical, and process variables, such as flow, can be easily detected using vibration analysis. Using the tips and techniques in this program, you can begin to pinpoint the source of problems in determining severity. We are confident that the tips and techniques in this program will help you understand how vibration analysis can accurately assess machinery condition and give you the ability to increase your competitive edge through increased quality and avoid costly failures that impact your bottom line. CSI offers training courses on nearly 30 related topics at our state-of-the-art training labs. We teach our courses across the U.S. and around the world. Books, manuals, videos, and posters are available to help you accomplish your goals. We look forward to helping you achieve success in your future endeavors. Thank you for joining the thousands who have selected CSI Training and recognized us as the world leader for training and educational products relating to PDM and RBM strategy. For information on these or other CSI training videos, books, manuals, posters, or classes, call area code 615-675-2400, extension 237. CSI Training offers state-of-the-art benchmark training for 28 different courses, more than 200 times a year in Knoxville, Houston, regionally and internationally, on topics including single and multi-channel vibration analysis, slow speed analysis, oil analysis, thermography, acoustic analysis, as well as product-specific classes. Other courses include correction technologies such as alignment and balancing, and root cause failure topics. CSI Training is also recognized as the leader in industry certification, offering multi-level development and certification paths for various crafts and skills in the PDM and RBM field.